Hello, today we are going to present to you multi-objective reinforcement learning, or MORL for short. My name is Fraser Baker.
And my name is Jeremiah Greer.
And our advisor is Dr. Fred Annickstein with the Department of Electrical Engineering and Computer Science at the University of Cincinnati. This is our senior design project. So what is reinforcement learning? It's learning by reward and punishment. So it actually came out of some of the early psychological studies on how humans learn, and now we're applying it to computers. So in computers, oftentimes you have large matrices that represent equations that compute values, and you can alter these equations to get different results, and in the case of reinforcement learning, you can boost the coefficients in these matrices when you see that they're producing better results, more accurate results for a machine learning model, or you can decrease them, and that's kind of the punishment is decreasing, the boost is the reward, and that's how you do reinforcement learning in a computerized machine learning model.
So what is multi-objective optimization? Well, as stated before in reinforcement learning, there's only usually one performance measure at which you determine how well something is learning and performing. And when it's performing well, you tend to reward it, and it's performing poorly, you tend to punish it. So in multi-objective optimization, we actually have multiple measures of success. So what that means is that we have multiple functions that we wish to reward and punish depending on their behavior. This can lead to some problems when rewarding one function actually causes worse behavior in another function. So it's a very complex balance to try and maintain.
So here's what we're doing. Reinforcement learning involves learning a task through feedback based on its performance and can be expanded to include multiple measures of performance, requiring multi-objective optimization. We seek to find a novel multi-objective optimization method for use in reinforcement learning.
Current methods involve linear combinations of reward terms, but balancing their weights has been difficult. Instead, we plan to use filter methods as an alternative method of multi-objective optimization.
We'll be testing our filter methods on OpenAI's MuJoCo Gym and compare our results to those using linear combination for multi-objective optimization. We will also examine alternative methods of feature selection, such as genetic algorithms.
Finally, we hope to show generality and demonstrate real-world benefits by applying our work to other data sets.
So as a data scientist, I want to enhance feature selection so that I can increase the accuracy of my machine learning models.
And as a robotics engineer, I want a better method of multi-objective reinforcement learning so that my simulated and real robots' performance improves.
And as a researcher, I want to utilize an improved multi-objective reinforcement learning model so that I can extract more information from my data than was previously possible. So here we have a diagram showing kind of the workflow that a researcher or engineer would go through. They can put their data into our feature selection models, which will include models of filter methods and models using genetic algorithms, and that will generate a feature selection result data set. And they'll be using the results of that feature selection as well as the original data in the reinforcement learning part of our use case diagram here. So the reinforcement learning part will use TensorFlow neural networks to implement the deep learning network. But then we will run k-folds validation on this neural network to show how well it is performing. That is, how is the accuracy, how is the sensitivity, etc. And all of this is being done to accomplish our problem statement, where we seek to find a novel method of multi-objective optimization for reinforcement learning.
So here's a more detailed view of the MORL system. It has two aspects, feature selection and reinforcement learning. In feature selection, we can use either filter methods or the genetic algorithm. In filter methods, we'll evaluate the usefulness of features and eliminate features at some threshold, and then run reinforcement learning with those features. In the genetic algorithm, we'll randomly select certain features, evaluate those features by either k-folds reinforcement learning or by filter methods, and then select the best features and mutate and generate new ones in a hope to repeatedly do this and eventually get a very good set of features. In reinforcement learning, we'll use TensorFlow reinforcement learning, where we will train a reinforcement learning network on these features, adjust the weights based on positive and negative reinforcement, and repeat this for all the training data. In k-folds validation, we'll shuffle the data and split it into k parts, one of which will be for testing, and k-1 parts will be for training. We will evaluate the results of the reinforcement learning model, and we will repeat and summarize this for the k different testing parts, thus reiterating our desire to find a novel method of multi-objective optimization for reinforcement learning.
And so for the specific implementation details for our filter methods, this will really be a pre-processing step where we will evaluate the usefulness of different features of the data using a variety of filter methods. These filter methods include the Pearson correlation, linear discriminant analysis, ANOVA algorithm, and the chi-square metric, all of which are common statistical methods, but we'll be applying them to this feature selection process. And we may end up designing our own to improve on these other methods if we find that necessary. In addition, we will explore the use of genetic algorithms for this process, where we'll repeatedly test features and evaluate them, applying mutation and crossover operations repeatedly until the score converges, at which point we'll stop the genetic algorithm process. And for these purposes, we'll be using the Python packages Pyvolution and Deep. In reinforcement learning, we'll actually be using the selected features in constructing a deep neural network, for which we'll be using TensorFlow. TensorFlow is a recent project done by Google to really make deep learning and these deep neural networks more accessible and easier to implement. As far as training and testing, we'll be using the MuJoCo gym from OpenAI, which is a simulated robotics gym environment where our algorithms and our methods will be able to be easily visualized as a 3D robot simulation. We'll also plan to apply this to some real-world data using the Your Mapper crime score and Google Maps to map out crime over different regions geographically, as well as a bioinformatics data set that relates to metalloproteins and proteomics. The last two of these will take a lower priority to the MuJoCo gym as it has a very nice visualization, and we are limited on time for this project. For the k-folds validation, we'll be implementing that using Python, scikit-learn, and other Unix tools. It's a fairly simple algorithm to implement, so it would probably be easier for us to just do that sort of manually. And all of this, again, will come together to satisfy our problem statement, which is that we seek to find a novel method of multi-objective optimization for reinforcement learning.
So what we've done so far is dedicated a lot of our time to the planning process. We've created a variety of user stories and design diagrams as requested for the class by Dr. Enigstein. We've created a timeline and issues/tasks to kind of organize our work for the rest of our time. We have also organized a GitHub page for our project to help increase kind of public viewability, and we have also created a logo. In addition, we've begun working on literature review, and we've started reading articles for the literature review, and we've also started gathering libraries to simplify the implementation of genetic algorithms and reinforcement learning.
So that leaves us really with development of the algorithms themselves and development of a CLI tool, as well as a GUI tool to help us make this extensible and usable by other scientists who might not be as computer savvy. This should also involve a visualization of the test results. And that also means that we'll need to be testing our project on different data sets as mentioned earlier. And then of course we need to create visual aids such as posters or presentations and write this up as a paper to document our progress and our scientific process, and then disseminate that through the Senior Design Expo and potentially other research expos as they are applicable. So yeah.
And here is an effort graph for the tasks we've created for this project. As you can see, for the majority of the tasks, we'll be attempting to put in about equal effort. This decision was made because we tend to work a lot together and we tend to work fairly collaboratively. So this will be a lot of pair programming type work and a lot of intercommunication within the team. And this is feasible because we are such a small team and we also happen to live together, so it makes meeting pretty easy.
So if you're interested in following our progress as we go along, please check out our project on GitHub. The link's right there. It's part of the Deepwater Discord group, which Jeremy and I formed. This is kind of our flagship project on GitHub. So please check it out and let us know if you have any comments on there. Thanks.